Every device you own, from a smartphone to a workstation with a Core i9 processor, operates on a foundation of strict, deterministic logic. Information is routed through discrete paths of binary ones and zeros. The physical limitation of this architecture is that classical systems must process those binary bits sequentially. They compute step by step. This sequential processing hits a mathematical wall when confronted with massive computational tasks, specifically the factoring of the colossal prime numbers used in modern cryptography. Because processing power scales linearly with each added classical bit, factoring those numbers on a conventional supercomputer would take millions of years to complete. A quantum processing unit functions through a mathematical framework separate from the clock speeds of silicon. This layout contrasts the two architectures. On the left, deterministic silicon. On the right, a quantum processing unit housed in a highly specialized structure called a cryostat, which physically governs quantum bits, or qubits. Quantum advantage works by replacing strict Boolean logic with the probabilistic mathematics of quantum mechanics. Solving these massive problems requires transitioning from the certainty of bits to the probabilistic mechanics of quantum states. Popular explanations often compare a qubit to a spinning coin, something rapidly blurring between heads and tails. That analogy fails to capture the exact physics required to actually engineer these systems. This is a Bloch sphere. Physicists use Dirac notation to map quantum states geometrically onto this 3D model, placing the classical 0 state at the North Pole and the 1 state at the South Pole. A qubit in superposition is defined by a state vector, psi. It exists as a linear combination of those two basis states. The variables alpha and beta represent complex probability amplitudes. The sum of their absolute squares must always equal exactly 1. While the system remains unmeasured, these amplitudes do not represent a hidden, predetermined binary value. They represent a continuous, fluid probability distribution. This changes due to the measurement postulate. The act of observation forces the isolated quantum system to interact with the macroscopic environment. Upon measurement, the wave function instantly collapses. The qubit yields a definitive 0 or 1, with the result strictly governed by the probabilities encoded in alpha and beta. A single qubit leverages a vast mathematical space of continuous probabilities to run its calculations, collapsing into a deterministic answer only at the point of output. A single qubit mapping probability vectors has limited computational utility on its own. Scaling a QPU requires a property called entanglement. When two or more particles are entangled, their quantum states become mathematically linked into a single joint wave function, forming a tensor product. Because the states share a joint distribution, modifying the mathematical state of one qubit instantly updates the entire system's probability distribution, no matter how far apart the physical qubits are separated. This structural link creates a severe deviation in scaling limits. Adding a classical bit adds exactly 1 unit of processing data. Adding an entangled qubit scales the system exponentially. This chart tracks that divergence. 1 qubit holds 2 amplitudes, 2 qubits hold 4, resulting in a state space governed by the function 2 to the power of n complex coefficients. At just 50 qubits, the system can concurrently hold and manipulate 2 to the 50th power complex values, well into the quadrillions. This exponential state space maps directly to high-dimensional datasets, where variables interact simultaneously. It allows a QPU to find patterns in agricultural commodity fluctuations or computer vision data that are mathematically invisible to linear systems. Entanglement provides the exact mathematical framework that transforms localized physics experiments into exponentially scalable processing engines. Operating in a 2 to the power of n state space introduces an immediate consequence for modern cybersecurity architectures. Protocols like RSA encryption are secure specifically because sequential linear processors take an impractically long time to factor massive prime numbers. Shor's algorithm is a specialized quantum protocol built to navigate that state space, using superposition and entanglement to factor those exact primes. This diagram shows a standard classical search. The system evaluates the dataset linearly, testing potential factors one by one. Shor's algorithm bypasses the linear search. It applies a probability wave across the entire dataset simultaneously. Constructive interference amplifies the peaks to reveal the correct factors, while destructive interference cancels out the incorrect answers. Using this interference mechanism, a sufficiently powerful QPU factors massive prime numbers and cracks RSA encryption in a matter of hours. Intelligence agencies and security researchers are actively building post-quantum cryptography to secure data against these exact algorithms. Quantum mathematics represents an active structural vulnerability to the protocols maintaining global digital security. If the mathematical capability is exponential and the algorithmic threat is real, there is a clear physical reason QPUs are not running standard network tasks today. The barrier to deployment is a primary engineering limitation called decoherence. The probability spaces of superposition and entanglement are hyper-fragile. Maintaining them requires absolute, unbroken isolation from the macroscopic universe. Microscopic thermal shifts, localized vibrations, or ambient electromagnetic noise will destroy the isolated state, triggering a premature wave function collapse. This corrupts the calculation before the system can purposefully execute the measurement. To mitigate decoherence, engineers must house the QPU inside a highly specialized cryostat, as shown in this blueprint. The thermal shielding in these units drops the temperature of the chip down to near absolute zero, making them colder than the vacuum of deep space. They are strictly limited to controlled laboratory and mainframe environments. Robust room-temperature silicon processors will continue to run standard operating systems like Parrot OS or Kali Linux for everyday computing. We are in the foundational stage of quantum engineering. Current research is heavily dedicated to stabilizing probability amplitudes and establishing algorithmic error correction. Quantum supremacy will likely manifest as a specialized tool for redefining the limits of mathematical possibility, existing alongside the traditional silicon found in consumer electronics.